So your second experiment would be on the characterization of active device such as power amplifier. So here we'll use VNA as well as spectrum analyzer. So we'll use VNA to measure the power gain of the amplifier, and we'll use spectrum analyzer for measuring both power gain and noise figure of the amplifier. So the objective of the experiment is to measure the gain and noise figure of an amplifier. So here you'll be using equipments like power supply. So we need a power supply to DC bias the amplifier. Without that, amplifier won't work in the proper region of interest. And you also need a signal generator which will give the signal to the power amplifier, and the spectrum analyzer can be used for measuring the gain as well as noise figure of the power amplifier. VNA can be used for measuring the gain of the amplifier. Device under test is the amplifier. So you have already learned about VNA in the last lab. This is how VNA looks like. And here we'll also use spectrum analyzer. So this the spectrum analyzer will be using it. So there will be a demonstration after this presentation. There it will be much more clearer. As I already told you in the previous class, spectrum analyzer can only measure the scattering parameters, but cannot measure the it can only measure the amplitude of the scattering parameters. It cannot measure the phase of the scattering parameter. VNA can do that. But here we'll use spectrum analyzer for measuring the noise figure of the power amplifier. So this is a vector signal generator. Here you can input what waveform you want to input to this device, at what frequency you can input that. So let's say you want to give a waveform at, let's say, 4 GHz. You have to key in 4 GHz, then you can give it to the device under test. And this is how the power amplifier looks like. Obviously, power amplifier is a two-port device. You have input port and output port. Whatever signal you give at the input port and what you get at the output port will be the amplified version of the signal you are giving at the input. That's your amplification of the power amplifier. So here you have pins here where you have to connect the DC biasing. Without DC biasing, amplifier won't work in the proper region. Okay, so the gain is obviously the ratio of the output by input. So whatever power you're giving in the input, if you are getting more power at the output, you have a gain. So amplifier has gain, and gain can be found out. So once you find out that ratio of power output by power input, you take 10 log of that, you get power gain. It's 10 log. See, it's not 20 log. So if it is 10 log, let's say power, what's the relation with the voltage? Power relation with the voltage is B square. So you replace this by B out square divided by B in square. Assume that impedance of the device is fixed. So in that case, B out square by B in square. So it's a square here. You bring it here, it becomes 20 log of. So it becomes 20 log of B out by B in for the gain in dB, but if it is in terms of power, is 10 log of P out by P in. So that should be very clear. You know? So many of the students get confused with that. So whenever you have B out by B in, you have 20 here because of the power is B square. You know? B square here. So B square you can take it outside, it becomes 20 here. So otherwise, when you take the ratio of P out by P in, it should be 10 log of. This is log to the base 10. No? So noise figure is defined as, let's say, maybe using this diagram here. Let's say there's a device here. You know the signal to noise ratio at the input and signal to noise ratio at the output. So SI is the signal power at the input, NI is the noise power at the input. SO is the signal power at output, and NO is the noise power at the output. If you know signal to noise ratio at the output and input, you take the ratio of those two. That's what we call noise figure. So SNR at the input divided by SNR at the output. If you are from communication background, you know what is SNR. SNR is the ratio of the signal power by noise power. So this is the SNR at the input and this is SNR at the output. The ratio of these two is called the noise figure, and obviously noise figure. So look at this. You can find out obviously noise figure from calculating all these terms here. So there's a major simplification here in the next slide. You know what is the gain of this device. So we can simplify this expression here. Noise figure is SNR input divided by SNR at the output. So now SNR at the input is SI by NI. What is SNR at the output? SNR at the output is basically SO by NO. What is SO? SO is the signal power at the output. That is basically equal to gain into signal input power. So you can replace that. So now you can cancel out SI and SI. In the numerator and denominator, what you get is noise figure is NO divided by gain into NI. So NO is the noise power at the output, NI is the noise power at the input, G is the gain of the device. So now you can calculate SI input, not SI, NI is simply KTB. K is the Boltzmann constant, T is the temperature in Kelvin. For room temperature, it's around 290 degree Kelvin, and B is the bandwidth. Depending on the bandwidth of the device you are considering, B is going to change. You can have a broad bandwidth, narrow bandwidth, so B is going to change. K is always fixed, Boltzmann constant. Temperature in Kelvin, room temperature is also always fixed, so only the bandwidth is going to affect this NI here. So you know what is NI, you know the gain of the, let's say you know the gain of the device DUT, you measure this N0, you can find out what is noise figure. Usually we can find out noise figure using the spectrum analyzer. In that case, we actually use cascaded device, noise figure of the cascaded device. We use the formula for the noise figure for the cascaded device. This is a series connection of a device 1 and device 2. When I want to measure the noise figure of an amplifier, I actually use this second device as a spectrum analyzer. This is the amplifier. First device is the amplifier, and is the spectrum analyzer. So if you have a series connection of cascaded device, device 1 and device 2, you can find out noise figure as NF1 plus NF2 minus 1 by G1. What is NF1? Is a noise figure of the first device. NF2 is the noise figure of the second device. It's also, G1 is the gain of the first device. What is G2? G2 is the spectrum analyzer, and spectrum analyzer usually have gain is equal to 1. Okay, so this is for the spectrum analyzer, this is for the amplifier, and this is the noise, overall noise figure is the NF. Overall noise figure of this cascaded series connection of amplifier and the spectrum analyzer is NF. So from using this relation, you can find out the noise figure. If you know what is the noise figure of this cascaded connection of the amplifier and spectrum analyzer, then that's NF here. And if you know what is the noise figure of this spectrum analyzer, and you know the gain of this first device, which is the amplifier, G1, if you know NF2, you know NF, which is the noise figure of the whole series connected to device, then you can find out what is NF1. NF1 is the noise figure of the first device. This is what exactly we are going to do in this experiment. Find out NF2, find out G1, and find out NF, and find out NF1. This is the noise figure of the amplifier using spectrum analyzer. So first thing, let's try to find power gain of an amplifier. So we need G1. No? This is a amplifier, the first device here, and we need G1. To find out G1, you can either use VNA or you can use the spectrum analyzer. So if you want to find gain of an amplifier using VNA, that is very simple. So first step is you do the port calibration, 2-port calibration that you have already done in the last lab. So whenever you want to use VNA, you do calibration first so that you can take care of all the cable losses and you can minimize the errors. Then don't forget, this is an active device. You need to give some DC biasing to the amplifier. Otherwise, amplifier will not work in the proper region of interest. So you call it, I think, active region of the amplifier. If you want to make sure that amplifier is working in the active region of the amplifier, then you have to DC bias it. So then you connect the input of the amplifier at port 1. Amplifier is a 2-port device. I've already shown you the device. It has port 1 and port 2. Input port, you connect to port 1 of VNA, and as you know, VNA has 2 ports, port 1 and port 2. The output 1, you connect it to the port 2 of the VNA. Then you just measure S21. S21 is the transmission coefficient. From there, you can get the power gain of the amplifier. S21 square is the power gain of the amplifier. S21 square is the power gain of the amplifier, and S21 is the voltage gain of the amplifier. This should be voltage gain. So it should be square here. So you can also measure this power gain of the amplifier using spectrum analyzer. So now what is the procedure for that? So here, as I already told you, VNA has an inbuilt source inside the VNA. You have a source, but the spectrum analyzer doesn't have any source. So you need to give some signal to the device. So you connect the signal generator output to the spectrum analyzer, and first, just like what you have done for calibration for VNA, you need to do similar to that here. So you have to take care of the cable losses and other losses. First, calibrate and normalize the spectrum analyzer so that same power is supplied to the signal generator. So you are using cables which are actually replacement wires of low frequency. So you need to calibrate the spectrum analyzer also at the beginning. So there's a procedure for that. Then you properly bias the amplifier, then apply the input signal. So here, since spectrum analyzer doesn't have any source inside, inbuilt source inside, you actually connect the power amplifier to the signal generator. That will give the source to the power amplifier. And you also properly bias the power amplifier and connect the output of the amplifier to the spectrum analyzer. Now spectrum analyzer will measure the power gain. So you can find out power input, power output minus power input is the power gain. dBm means dB per milliwatt. So the reference power would be milliwatt. So dBm, dBi, all these parameters you should be very clear, understand. You can have dB watt also, then reference power is the watt. dBm means your reference power is milliwatt. So we have the power gain of the amplifier. That was your G1 in the previous equation. We have G1. So we also want to know what is NF2. That is the noise figure of the spectrum analyzer. How do I do that? That's very simple steps here, 3 steps here. First, what you need to do is you need to connect a 50 ohm load at the input port of the spectrum analyzer. Just connect the 50 ohm load to the input port of the spectrum analyzer. So you know that 50 ohm is a match load. Then you find out what is the N naught in the spectrum analyzer. You have N naught. Let's say if you want to find out NF2, how do you find out? You find out NF2 as N naught by G2 Ni. What was G2 gain of the spectrum analyzer is 1. Ni was KTB, so you can find out. So you know what is N naught, you know what is G2 is 1, Ni is KTB, N naught is what you are reading. Now after connecting the match load to the spectrum analyzer, you can find out the noise figure of the spectrum analyzer, which is NF2. So it will simply be N naught by Ni. So you have NF2, you have G1, you also want to find out NF of the cascaded network. So you can do the series connection of the amplifier and the spectrum analyzer. Device 1 is amplifier, device 2 is spectrum analyzer. So here you connect 50 ohm load at the input of the amplifier and note down the N naught in the spectrum analyzer. So after you do that series connection of amplifier and the spectrum analyzer, you connect input port of the amplifier with match load. Then you note down what is N naught in the spectrum analyzer. So now you know that N naught divided by gain into Ni gives you the noise figure. So noise figure is N naught by gain divided by gain into Ni. Ni is KTB. Gain here is basically it's a cascaded series cascaded connection of device 1 and device 2. So total gain would be G1 and G2, but we know that G1 is already calculated, but G2 for the spectrum analyzer is 1, so gain will simply turns out to be G1 now. So you know G1 from the previous experiment, you can use that and find out what is the noise figure of the cascaded connection. Then you can, from there you can find out what is the noise figure of the amplifier. So how do I find the noise figure of the amplifier? Once I have NF, G1, and F2. So NF2 is the noise figure of the spectrum analyzer. G1 is the gain of the DUT amplifier we are using as a DUT here. I know what is the NF for the cascaded connection of amplifier and the spectrum analyzer. Everything is known except this NF1 here. From here you can find out what is NF1, which is the noise figure of the amplifier. Okay, thank you.